The liquids will also flow if shearing forces are applied. If shearing forces are applied, the liquids can also flow. For example, if a liquid in a beaker is stirred well, then it rotates in the beaker. It rotates in the beaker. The rotation continues as long as the liquid is stirred. When the liquid is stirred, a force is applied tangential to or shearing forces are applied on the liquid layers, and the liquid layers at the center will move with high speed, and as we move towards the edge of the beaker, the speed of the liquid layers decreases. So less velocity. The layers near the center will have more velocity, and the layers towards the surface of the beaker will have less speed. When we stop stirring, we notice that the liquid comes to rest after some time. So from this, what we understand is, we can explain this by imagining that the liquid layers will apply dragging forces one on another. For example, the liquid layers which are moving with high speed at the center, they apply dragging force on the layers in contact with them, and these layers try to resist the motion, hence they apply a drag on the high speed layers. So this drag can be compared to the friction in mechanical motion. For stirring the liquid, we use energy. This energy will appear in the form of kinetic energy when the liquid is in motion. When it comes to a stop, the kinetic energy will appear as heat energy. So like this, we can explain this phenomenon. Velocity gradient. To understand this concept, let us imagine the flow of water in a canal. If we imagine the water flow as though it consists of different layers, the bottommost layer, which is in contact with the ground, can be considered to be at rest, and the topmost layer moves with highest velocity. It flows with highest velocity. As we proceed from bottom to the top, the velocity of different layers increases with increase in height. With the increase in height from the bottom to the top, the velocity of the layer increases. Let us consider two layers at height x and x plus dx. Let us consider two layers at a height x and x plus dx. Let us suppose the velocities of these two layers. Let us suppose the velocity of the layer at a height x is v, and the velocity of the layer at a height x plus dx is v plus dv. That means the velocity difference of the layers is dv. The velocity difference of these two layers is dv, and their separation is dx. When the water flows in a steady state, this dv by dx is a constant. This is known as velocity gradient. A relation for viscous force. The viscous force depends on the area of the layer, and the velocity gradient. Viscous force is the force applied against the flow of the fluid, against the flow of the fluid. And this force is directly proportional to the area, surface area. This force is directly proportional to the surface area, and it is also directly proportional to the velocity gradient. It is also directly proportional to the velocity gradient, but it is opposite to the direction of velocity. It is opposite to the direction of velocity. By combining the two proportionalities, we get, if we imagine that area of a layer is A and its velocity gradient is dV by dx, and the velocity gradient of the fluid is dV by dx, then F is proportional to A and F is proportional to dV by dx. F is proportional to A and F is proportional to dV by dx. By combining these two proportionalities, we will get F is proportional to A into dV by dx. A into dV by dx. Since viscous force acts opposite to the velocity, opposite to the flow of the fluid, we indicate this with a negative sign. We indicate this with a negative sign. So we write F is proportional to minus A dV by dx. And this proportionality is replaced with a constant eta. This proportionality is replaced with a constant eta. Hence, the relation for viscous force is equal to minus eta A, eta into A into dV by dx, minus eta into A into dV by dx. Eta is known as coefficient of viscosity. Eta is known as coefficient of viscosity, and it can be defined as the force acting normally over unit surface area when the velocity gradient is unity. Like this we can define the coefficient of viscosity. Units of eta. SI unit of eta is Newton per meter square into second, or Pascal second. Celsius unit is poise. One poise is equal to 10 to the power of minus 1 newtons per meter square into second. Eta by rho, where rho is the density of the fluid. Is indicated with mu. And it is called coefficient of kinetic viscosity. And eta is measured with the unit meter square per second. Mu is measured with the unit meter square per second in SI system, and it is measured in Stoke in Celsius system. One Stoke is equal to 10 to the power of minus 1 meter square per second. Variation of coefficient of viscosity with temperature in liquids. This viscous force arises due to the molecular force of attraction. As the temperature increases, the molecular separation increases, and thereby the molecular force of attraction decreases. Hence, the viscous force decreases, and thereby the coefficient of viscosity decreases. So the coefficient of viscosity, decreases with increase in temperature, decreases with increase in temperature in the case of liquids. In the case of liquids, variation of coefficient of viscosity with temperature in gases. Variation of coefficient of viscosity with temperature in gases. In gases, the viscous force arises due to the transfer of molecules. As the temperature increases, the momentum of the molecules increases. And the viscous force depends on the transfer of momentum. More is the transfer of momentum, more will be the viscous force. Hence, the viscous force increases, or the coefficient of viscosity increases with the increase in temperature in the case of gases. In the case of gases, the coefficient of viscosity increases with increase in temperature.